Okay, so here we're starting with an asymmetric alkene. When I say that it's asymmetric, is that there's different substitution on both sides. So if you're adding an asymmetric group to it, you have to consider which way it's going to go. So I believe we did a little bit last time. So I showed you guys the addition of HX. So X in most cases in this class is a halogen. And this was the case where you got the Markovnikov addition. The word that Alan said I was making up. I was not making this up. So here we get Markovnikov addition. And the way we identify the Markovnikov product is X goes more substituted. So this was the Mark product. So Mark addition. Okay. We're going to see also during this section here, if you actually change the conditions here to be ROOR type compound, this is a peroxide. So I want to mention here, this is the peroxide. So it could be hydrogen peroxide or an organic peroxide. Basically, you have an O single bond O in there. This gives you anti-Markovnikov addition. Like that. So this is anti-Mark addition. If you're worrying about mechanisms here, we are going to go over Markovnikov addition of HX. We will cover anti-Markovnikov addition mechanism after the test. We actually wait for that one for the radical chapter, because that is a radical mechanism. That was where you had the odd electron count. Okay. Neither one of these is syn or anti. These both have a intermediate that's going to lead to racemization of the product. So you're going to have the same situation here, is that we get addition of H, we get a carbocation. After the carbocation forms, it's just an SN1 after that. So how we get the carbocations, what's different here? Okay, so another situation we're going to do is if this is in water, so we have HX and H2O. We saw earlier today that this is basically hydronium, right? So if this reaction is happening in hydronium, we get Markovnikov addition like that. Okay. The other way to do, there's going to be two ways to do this. We'll see if we can probably get it started today, maybe, is the oxymercuration demercuration reaction. So this was mercury, acetate, and water, and THF. That's the first step. The second step is NaBH4. That was called the oxymercuration demercuration reaction. So oxymercuration demercuration reaction. They give the same product. There is going to be a reason why you want to choose using H3O plus versus using this one. Has to do with carbocations. Okay. So are you guys feeling a theme here? Any ideas what the next reaction might be if we're following a trend? Maybe an anti-Mark addition of OH? Yep, so there's an anti-Mark addition of OH as well. All right, so this one is, this one fortunately has one main way to do it. This is the hydroboration oxidation. So this is BH3, and then the second step is an oxidation. It is NaOH and H2O2. And this will give you anti-Markovnikov addition of the alcohol group. And this one again, the name was hydroboration. That's the part where you're adding the bromine group on there. And hydroboration oxidation. These are the only ones that are going to be on the test.
So the 1 and 2, do they go up with the OH? Does it have a picture?
What do you mean? The numbers here?
The number, the next one up, the one that you did with the mercury?
These are the same product.
Okay.
So going this way, it's this or this does that. And we're going to see today why we need to make a choice. There are other numerous reactions. I would keep this page handy. I'm going to keep it in my notes, and we'll add to this when we get the other reactions. So the reaction. So I want to mention that there's stuff here. If you're doing the activity sheet, there's things that we're not going to do. These were like the bromine addition. We're not going to do that, and we're not going to do any of the redox stuff because I want time for the redox reaction. You'll understand why when we get there. It's a lot of carbon counting, and basically what redox allows us to do is break molecules in half into fragments. And yeah, we've got to get this stuff under control first before we start doing that crazy stuff. So these are the only addition reactions we're going to have on the test. Yay! This is about half of them. So I'm being kind of nice here. This is about roughly half of the reactions. Maybe less than half, actually, now that I think about it. After we are done with the addition reactions, I'm basically going to throw them all in one big pot together and stir it, and then we're going to start doing some real problems. Because then we'll finally be able to do some real organic chemistry problems. It's just like what we were doing earlier this semester where we had to build up to reactions. We're finally building up to being able to do some real organic chemistry problems. So by the time at the end of the year, you'll have your first OCHEM problem, which I think are synthesis questions. How do you go from compound A to compound Z, basically? We'll get there. I'm getting a little bit ahead of myself. All right, so addition of HX. Let's go over this real quick. Addition of HX to alkenes. This is not too bad, guys. It really isn't, at least for this part here. So it turns out that alkenes, the pi bond is nucleophilic. So I'm going to add these little comments in here. I think I'll use blue. So pi bonds in alkenes plus alkynes are nucleophilic. They are nucleophiles. So you can go ahead and have them jump out and grab. They can act as a base and grab an H. That's going to be the case in a lot of these problems here, like so. So now we have a situation of where does the plus charge go? I believe we went over this last time. So if the new H goes here, and I want to go ahead and circle the new H, so it can be one of these over here, we get a more substituted carbocation. So here, the general gist you want to go with is H goes less substituted. So it's going to go on the end here. And the result of that is your plus charge goes more substituted. This whole thing here kind of summarizes Markovnikov's rule. This second little this comment right here, that is essentially Markovnikov's rule. And Markovnikov's rule states that the reaction proceeds such that the more stable carbocation is formed, which is what we're basically saying by mentioning it goes more substituted. At this point, the rest is essentially SN1. So at this point, rest is SN1. So any considerations we had during SN1 apply here as well. So as you can probably guess, carbocation rearrangements are a thing still. Anytime all year long we have a carbocation, we have to worry about rearrangements happening. That's what, and I mentioned before we first started going over there, that's why we kind of avoid them in general when doing reactions in the lab. They give multiple products. All right, so just like SN1, we saw in the SN1, we get that. So then you end up with the more substituted product. So more substituted product And we like to call that the Markovnikov product. The Markovnikov, not made up. Okay. Markovnikov's rule states, once again, that the reaction will proceed such that the more stable carbocation is formed. So Markovnikov's rule, addition of HX will proceed with the most stable carbocation intermediate. So even though like some of the other mechanisms do not have a carbocation mechanism, in general, the more substituted version of the product is just in general referred to as the Markovnikov product. Even if it had a different mechanism, we still refer to it the same way. Okay, so I want to go ahead and show the same reaction now with addition of hydronium. So here we have H3O plus instead. Oops, back up just a minute here. I did introduce some new words here last time with this stuff. If you have the notes from last time, I mentioned words such as stereoselective and regioselective. So when we're referring to things as being like inversion of stereochemistry or racemization, that is, you're saying if the reaction is stereoselective or not. If you're referring to Markovnikov versus anti-Markovnikov or Zaitsev versus Hoffman eliminations, you're referring to regiochemistry then. So one of them, like the region of the molecule where the group goes, and then that's for regioselective. So this reaction is regioselective, but it's not stereoselective. And it's not stereoselective because we have a carbocation in the middle. Anytime you have a carbocation, the reaction is not stereoselective, you get a racemic product. And that was just the same, a more official way of saying the stuff that we were talking about back since SN1. All right, so on the task at hand now, this mechanism starts the exact same way. Is instead of attacking the HX, it has the hydronium to attack. We get the more substituted carbocation. And now water can come in and attack like this. And now we have an intermediate where people often forget about. Do not jump the gun. You are not quite done yet. We have the extra H to deal with. Like that. Because water has two H's on it. Any ideas on what I should do next?
Another water.
Another water. And if you said it's going to act with the base. And this should deprotonate the alcohol now. So deprotonation step, giving us the final product. And what's the other product here? Hydronium. Okay. So if you're running a reaction that has a catalyst, you must show it being used and then it being remade. I will be very particular about that when we have reactions mechanism with the catalyst on a test. One general thing that I don't think I mentioned to you guys yet, that now that I'm thinking about it, is you can actually kind of tell if your mechanism is on the right track. If your mechanism is an acid, you're either going to have no charges or positive charges on the whole mechanism. If your mechanism is in base, you're going to have all negatives in your mechanism. You can kind of use that as a general idea if you're doing this correctly. There's no possible way for me to get a negative charge in this mechanism and it not be something wrong with it. All right. So let's go ahead and take a look at a situation where a little bit different structure here. Actually, let's make it part of a ring. And I don't know. Actually, let's put this here. Okay. Actually, we'll come back to this one here. I want to do a different example. Let's do this one. All right, so here I want to go ahead and do the addition with H3O plus. And for we have plenty of practice, we'll go ahead and do the mechanism. So first things first, and you're going to see this all year long just about too, is if we have a catalyst, the first step in the mechanism is often an acid-base reaction. So acid-base here, so double bond. You guys notice where I'm putting the arrow from? You notice this on all of them so far? I'm showing it from the middle of the bond. I'm being particular about that. It's from the middle of the bond. It is the pi bond doing the chemistry here, not one of the atoms. Okay. Here we get the more substituted carbocation, so it goes here. And based off of what you guys remember from SN1 stuff, what can happen next? A methyl shift can happen. Yes, exactly. So methyl shift happens like this, and then now the plus charge is over here. The methyl is now moved, and now the rest of the mechanism is basically the same. So water can then attack, boop, like that. And then here we have, don't forget about Rudolph. Looks like Rudolph, kinda. Like a little reindeer. All right, so then last step here, deprotonation to give us the catalyst back and a neutral product. So boom, boom, like this. Okay, so earlier, just today, I did show you guys the alternative method. That was the oxymercuration demercuration. The point of it is to not get rearrangements. So the oxymercuration will proceed the exact same way without any rearrangements. So I want to go ahead and show that now. You guys get, looks like everybody's still writing this one still. We had a second to get caught up. Huh? Oh, you're right. You're gonna mark me off for that. -2. All right. So when I took organic chemistry, our teacher told the TA, at a university, so we had TAs. He told the TA to, for every question that had a mechanism, he would mark us off 1 point for every lone pair missing until you got to the value of the question. So yeah, if you didn't have every single lone pair, it would be 1 point per each. Yeah, I had questions where the mechanism was right, but I got 0 points on it because all my lone pairs were missing. So I learned that after the first test to include lone pairs. I'm not that Nazi. I mainly look for the ones that are relevant that you included. All right, so let's go ahead and do the same one again. This time we're going to switch it to the oxymercuration demercuration.